This is your AP exam review number 4. So this one is about exploring bivariate data. So bivariate just means two variables. And so we're going to look primarily at scatter plots, and then we'll move into residual plots. So to start off with, scatter plots are basically relationships between x's and y's, so x variables and y variables, that can be reasonably explained in terms of a linear function. So a linear function obviously being a line. So that is, whenever you graph it, you should see basically a straight line. So we are looking for the best fit straight line, or the line that closely represents the patterns of the dots in the scatter plot. And we want to be able to gauge whether the relationship between the variables is strong enough so that you can find and make use of the straight line and its meaning. So the first thing we're going to do with looking at scatter plots is we're going to talk about some general patterns that you might see. So a positive relationship is going to be a scatter plot that has a very obvious positive slope. So you're going to have to kind of think back to like the stuff that you learned early on in your high school math career. And so when we talk about slope, you've got two types of slope that you really see. You've got positive slope. So this would be when you had a line that went basically down on the left, up on the right. And you have negative slope, which is where you go up on the left, down on the right. So the first one is a positive relationship because we obviously have a positive slope to our points. And the second one is a negative relationship because we obviously have a negative slope to our points. The last one here is a no relationship. So we can't make a straight line from these points, or we don't see a linear pattern in these points. So once we discover whether we have a positive relationship or a negative relationship, then we talk about how strong a relationship we have. So if we see that our points are very closely clustered together and it has a positive slope, then we say that this has a strong positive linear correlation. And then if we see that our points are going still in a positive direction, but they seem to be a little bit more spread out, then we say that we have a weak positive linear relationship or correlation. Same thing with negative relationships. So if we see that our points are our scatter plot dots are very close, but they seem to be going down, then that means we have a strong negative linear correlation. And if we see that our points are kind of spread out a little bit, but still going down, we have a weak negative linear correlation. So in addition to being able to talk about whether or not you have a positive, negative, or a strong or a weak relationship, you also want to talk about, is there clustering? Does there seem to be pieces that are kind of like grouped together? And do you have outliers? So, for example, in your first example that you have to do any work with, it says an experiment was conducted to note the effect of temperature and light on the potency of a particular antibiotic. One set of vials of the antibiotic was stored under different temperatures, but under the same lighting, while the second set of vials was stored under different lighting, but under the same temperature. So, you've got your two scatter plots here. So you've got the temperature. So if you look at your x-axis on the first one, your x-axis is talking about temperature. It looks like each one of these lines represents 10 degrees. And then you have on your y-axis potency of the antibiotic, which just has 1. So you've got your points. You see that you have definitely a linear pattern, definitely a negative linear pattern, and then you've got this like one random point down here at the bottom. So this one point seems to be an outlier because it's outside of the pattern. So a possible explanation is that maybe this antibiotic is more potent at lower temperatures, but only down to a certain temperature at which it drastically loses potency. Okay, in our second scatter plot, we see that our x-axis has changed now to light intensity, and our y-axis is still potency. So each of these lines represents a tenth or 0.10, And so our y still just has the potency at 1. So we can see that we have like definitely a group here, and then we have a group down here. So it appears in the second scatter plot that you definitely have the 2 clusters, but it appears that below a certain light intensity, the potency is 1 value, while above that intensity it is another value. So in each of the clusters there seems to be no association between intensity and potency. So you can see we've got a cluster here where our light intensity is kind of low, but our potency is pretty high. And then we've got a cluster here where our light intensity is much higher than it was in the beginning, but our potency seems to be a little lower. All right, correlation and linearity. So although a scatter diagram usually gives a visual indication whether a linear relationship is strong, in most cases it is quite difficult to visually judge the specific strength of a relationship. So for this reason, there's a mathematical measure that we call correlation, or sometimes you'll hear it called correlation coefficient, and we denote that by using the letter R. So one thing that is important to remember is that this correlation does not mean that you are creating a cause and effect relationship. So you cannot explain a particular relationship as cause and effect just because the correlation seems to be high. So correlation only is going to measure the strength of a relationship, a linear relationship. It's not going to tell you cause and effect. So the value of R, or your correlation coefficient, is always going to fall between -1 and +1, with -1 indicating a perfect negative correlation and +1 indicating a perfect positive correlation. It should be stressed that a correlation at or near 0 doesn't mean there isn't a relationship between the variables. It just means there's not a strong linear relationship, or there's not a linear relationship. There may still be some sort of strong nonlinear relationship, and we'll get into nonlinear relationships later. So you've got some examples here of correlations, and so on the first one, you've got a perfect positive correlation. So you can see that your scatter plot dots are all in a perfect line and all in a perfect positive line. So our R is equal to +1. On the second one, we can see that our dots are definitely still going in the positive direction, and we can see that they are close to the line, but they're definitely not as close as they were to begin with. So this R could be like 0.8. And then in the third example, we see that our dots are still going in the positive direction. However, they're much more spread out. So we can expect to have a number that's still a positive number, but definitely much lower than 1. The fourth is just a no correlation, or an R that's equal to 0. So we can tell that there's no linear relationship as far as being a positive or a negative. They're just kind of like randomly scattered. We have a low negative correlation here, so we can see that our dots are definitely going down, and we can see that they are spread out. So a -0.3 is a possibility here for our R value. We can see on the next one, we're going down. Our points are a little closer, and so that would be like a -0.8. And then a perfect negative correlation would be our dots are perfectly lined up, and our R value would be equal to -1. If you'll think back to when we talked about scatter plots, that was in like Unit 3. And so a lot of what we focused on in Unit 3 was talking about observed values and predicted values. And so when we talked about our predicted values, we talked about our predicted values being our y hat. So our y hat was equal to our predicted, and our y was equal to our observed values. So y was observed. Okay, so the coefficient of determination, or R squared, is the ratio of the variance of the predicted values, y hat, to the variance of the observed values, y. So we can say that R squared gives us the percentage of variation in y that is explained by the variation in x. So if you'll think back to when we talked about R squared, remember we talked about how R squared was always like a script. And you would say basically like this percentage of variation is y is explained by the variation in x. So remember that r squared is like a script. So you're going to use that script every single time that you describe your coefficient of determination. So while the correlation r is given as a decimal between -1 and +1, the coefficient of determination, or r squared, is usually given as a percentage. So an r squared of 100% is a perfect fit, with all the variation in y being explained by the variation in x. So how large a value of r squared is desirable kind of depends on the application that you're working with. So scientific experiments often aimed for an r squared in the 90% or above range. However, if you're looking at for an observational study, then your r squared of 10% or 20% might still be informative to what you're trying to do. The least squares regression line is where we spent a lot of our time in Chapter 3. And so our least squares regression line basically was an equation for a line that was like our prediction line. And so the point of having that equation was that we would be able to predict the value that we thought was a possibility. Any x value that we wanted, we could predict what we thought would happen based on how the other points were behaving. And so because this is a line, then your equation that you were using for your least squares regression line was y equals ax plus b, or you may have chosen to use y equals a plus bx. And so remember, that was either option 4 or option 8 on your calculator. And right off, I don't remember which one is which, but you'll know whenever you see it because it'll basically look like that slope-intercept form. So this is in slope-intercept form, and that's another one of those math 1 terms from a long, long time ago. All right, so the thing about this line is once you got this line, this line will always pass through the point x bar, y bar, where your x bar is obviously your average or your mean for your x's, and your y bar is your average or your mean for your y's. So, this is a good picture here of how this particular line works. And so you are going to go through, so there's your point, your x bar, y bar, and then this is a point here that is an x value and a predicted y value. Remember, we talked about how y hat was a predicted value. And so that x is just whatever number you wanted to predict the outcome for. And so to find the slope, remember that your slope is your rise over run, or your change in your y values over your change in your x value. So again, going way back to Math 1. And so that's where these values are coming from. This is your change in your y values. This is your change in your x values. The slope, or what they're calling b sub 1, can be determined from the formula b sub 1 equals r. Remember, your r is your correlation, and or r times standard deviation of y over standard deviation of x. On example 4.2, following our advertising expenditures and total sales for 6 detergent products. And so you've got your X values, which are advertising costs in thousands. And then you've got your Y values, which are your total sales in thousands. And so you can see your numbers there. So what that means is for an advertising cost of $2,300, the total sales were $77,000. So predict the total sales if $5,000 is spent on advertising and interpret the slope of the regression line. And what is $100,000? What if $100,000 is spent on advertising? So this should say what if. Okay, so if we want to predict, if it asks us to predict, then that means that we want to get our least squares regression line. And so to get our least squares regression line, you're going to need to use your calculator. So to get, because you've got x values and y values, you're going to go to Stat, you're going to go to Edit, and you're going to fill in some values for L1 and L2. So we're going to remember, go to the top, hover over L2, hit clear, and then jump down, and it'll clear out everything in L2. Do the same thing for L1. And then you're going to put your values for your x's in your L1. So 2.3, 5.7, 4.8, 7.3, 5.9, and 6.2. And then your L2 is going to be your y values. So 77, 105, 96, 118, 102, and 95. Okay, so now, if we want to be able to get our least squares regression line, we're going to go to Stat, we're going to go to Calc, and we're going to go to Lin Reg. Lin obviously stands for linear. Reg obviously stands for regression. So remember, we talked about how there were two options here, 4 or 8. They'll both give you the same thing, but it just kind of depends on how you want to look at it. So I'm going to go with option 4. So if I go with option 4, I want to make sure I've got my x as L1, my y as L2, and then I'm going to go to calculate. So whenever you do that, you end up with your equation. And at the very top, your y equals ax plus b. So that's our slope-intercept form that we were talking about for our line from earlier. We can see our coefficients here. So our coefficient for a would be let's say 7.295, and our b would be 59.683. Now, your r squared, remember, is your coefficient of determination, and your r is your correlation. Remember, if those don't show up, you can always go to Second, Catalog, make sure that your diagnostics are on, so do alpha, and then the letter D, which is your inverse button. Alpha D. Alright, so then you're going to make sure that you go to Diagnostics, and you want to make sure that you hit Diagnostics on. So mine was already on, but just to show you how to get there. Diagnostics on, and then hit Enter. Alright, so now I'm going to go back and get all my information that I need. There we go. All right, so predicted sales if $5,000 is spent. Let's first write down what our equation for our regression line would be. So our prediction line, or your least squares regression line, is y hat equals 7.295x plus 59.683. Now remember, you could have it written the other way, and if you had it written the other way, it would just say y hat equals 59.683 plus 7.295x. Okay, so it's also important that you kind of know what your variables stand for. So your y hat, because y was our total sales, our y hat would be our predicted sales. And so our predicted sales would be 7.295. Our X was our advertising. So 7.295 times our advertising costs plus 59.683. Now it's asking us to predict the total sales if $5,000 is spent on advertising. Okay, so if our total sales is our predicted sales and our if we're spending $5,000, then our X, because our X is in thousands, our X would be 5. So to find out what our predicted sales are, we would say 7.295 times 5 plus 59.683. 96.683. All right, so when we do that, we find out that our predicted sales would be 96.158. Okay, so if our predicted sales are 96.158, remember that that's predicted sales in thousands. So essentially what that means is if $5,000 is spent, you can expect $96,158 in sales. Okay, it does ask us to interpret the slope of the regression line. And so remember the slope, if we have it in slope-intercept form, y equals mx plus b, that would be the piece that's in front of x. And so the piece in front of x was that 7.295. So what that 7.295 means is that for every extra $1,000 spent on advertising, the result on average would be $7,295 in added sales. And so the very last piece says, what if $100,000 is spent on advertising? So remember again, if it's asking us for $100,000, we have to think about what our X value would be at $100,000. And so if we're looking for $100,000, our X value is going to just be 100. So to find our predicted sales for that, we're going to still use that same 7.295. We're going to change our 5 this time to 100, and then we're going to still add that 59.683. And so whenever you do that, you're going to get 789.183. And so if $100,000 is spent on advertising, you can expect $789,183 in added sales. Now, should we put all of our weight in this? Like if this was our business, should we put all of our weight in this, that if we spent $100,000 on advertising, that we should get $789,183 in added sales? Not really. Is it something that you can use? Then yeah, sure. But is it something that you should put all of your weight in? Not necessarily. Remember, this is just a prediction. It's not what's definitely going to happen. All right, example 4.3. So a random sampling of 30 U.S. farm regions surveyed during the summer of 2003 produced the following statistics. So the average temperature in degrees Fahrenheit during the growing season, our X bar is equal to 81, and our standard deviation for X is 3. The average corn yield per acre is Y bar equals 131, and our standard deviation of Y is equal to 5. Our correlation is 0.32. Based on this study, what is the mean predicted corn yield for a region where the average corn growing season temperature is 76.5 degrees Fahrenheit? Okay, so maybe the easiest way to deal with this, because we don't have a whole lot of information, is to get a z-score for this particular temperature. So to get our z-score for that particular temperature, remember our z-score is equal to our x minus our x bar over our standard deviation. So our x, because remember it appeared like our average temperatures were our x's and our yield of corn was our y's. Our x that we're looking at for this particular problem is 76.5. Our x bar they gave us is 81, and they told us that our standard deviation of x was 3. So if you do that, you're going to get negative 1.5. So this means that 76.5 degrees Fahrenheit is going to be 1.5 standard deviations below the average temperature reported in the study. So with a correlation of R being equal to 0.32, we can basically say 0.32 times our standard deviation, negative 1.5, or our z-score, negative 1.5, will give us negative 0.48 standard deviations below the average corn yield. So, essentially, if we're doing that, we're going to take our average corn yield and we're going to subtract out 0.48 times our standard deviation of y to get 128.6 bushels per acre. Now, another way that you could have done this, you could have found the regression equation using the slope and then finding the y-intercept. And so if you remember back on my last slide, our slope was equal to our correlation times our standard deviation of y over our standard deviation of x. So in this particular problem, our correlation is 0.32, our standard deviation of y is 5, our standard deviation of x is 3, and so you would have gotten your slope to be 0.533. All right, to find your y-intercept, remember that your equation is y equals ax plus b, where our a is our slope. So we would say we're looking at 131, that's our y, equals 0.533 times our x value, which is 81, plus some value for b, which is going to be our y-intercept. When you work that out and you subtract this stuff on the other side, you'll get that your b or your y-intercept is equal to about 87.8. And so then, now that you've got your b or your y-intercept, that means that your predicted yield would be equal to 0.533 times, not x, let's make it your temperature. Plus 87.8. Now, the temperature that we're plugging in is 76.5, so you'd say 0.533 times 76.5 plus 87.3, and whenever you do that, you would find that your predicted yield would be 180 or 128.6. Now, when we talk about our observed values and our predicted values, the next natural thing in the progression is a residual plot. And so a residual is basically going to be the difference between the observed value and the predicted value. And so we always find the residual by taking the observed value and subtracting out what you predict to happen. So when the regression line is graphed on the scatter plot, the residual of a point is the vertical distance the point is from the regression line. So if you see the point to be on the top side of your line, like in this case on the top side of your line, then that means that our observed value was greater than our predicted value, which means that our residual here would be positive. If you find your observed value to be below your predicted line or your least squares regression line, then this would mean that you had a negative residual value. Okay, example 4.4. We calculate the predicted values from the regression line back in example 4.2. Your example 4.2 was about the advertising expenditures and the total sales for the 6 detergents. And so we had our X values, which remember was our advertising costs. And then our Y values were our sales. And so our Y hat, of course, would be our predicted sales. Predicted sales. And then our bottom row in our table here would be our residuals. And so I know it's the residuals because it's our observed Y values minus our predicted Y values. And so you've got those values there. So the first thing it asks us to do is find the sum of the residuals. So I've already calculated all the residuals for you. You just have to find the sum of them. So just add them up. So 0.5 plus 3.7 plus 1.3 plus 5.1 minus 0.7 minus 9.9. So if you do that, 0.5 plus 3.7 plus 1.3 plus 5.1 minus 0.7 minus 9.9, you're going to get 0. And that's always going to be the case. So anytime that you find the sum of the residuals and therefore the mean of the residuals, it's always going to be equal to 0. The standard deviation of the residuals is calculated as follows. So you'll see it as S sub E. Sometimes you'll hear it called the standard error, and that would be equal to the square root of the sum of the observed minus the predicted squared over n minus 2. And this gives you a measure of how the points are spread around the regression line. So when you're looking at the residual plot, you're looking for a definite pattern in the residuals. And so if you see a definite pattern in the residuals and you don't just have like a random scattering, then that means that you are, that a linear model may not be your best way to predict. It may be a non-linear model, may be a better fit than a straight line regression. So remember, you're looking for a random scattering of the residuals a little above and a little below to be able to use a linear regression. And you also want to see a balance between the positive and the negative residuals. So you want this balance between the positive and the negative residuals because they should always add up when you take all the residuals to give you 0. So you've got to have a little bit on the top, a little bit on the bottom to be able to get to that 0. So let's look at example 4.5. So suppose the drying time of the paint product varies depending on the amount of the certain additive it contains. And so you've got your X values as your additives in ounces. You've got your Y values as your drying time in hours. So using a calculator, find the regression line. And so we're going to start first by, remember, taking our X values, plugging them in for L1, and our Y values and plugging them in for L2. So I'm going to go Stat, Edit, clear out my L1 and my L2, and then plug in my new values. So x values are 1 to 10. L2 values, you've got 4, 2.1, 1.5, 1, 1.2, 1.7, 2.5, 3.6, 4.9, and 6.1. All right, we want to be able to get our least squares regression line, so we're going to go to Calculate. We're going to go to option 4 or option 8, depending on which one you want to use. Your X's were your L1s, your Y's were your L2s, and then you're going to go to Calculate. So we get that our regression line is y hat equal to 0.327x plus 1.062. Okay, so then it asks us to find our residuals. So to find our residuals, for x being equal to 1, our y was 4. Our predicted y, I'm going to go ahead and give this to you, would be, actually I'm going to have to work this one out. You would have 0.327 times 1 plus 1.062. And so you'd have 1.389. So 4 minus 1.389. So then we're going to say 4 minus 1.389, and that will give you 2.61. So you do the exact same thing for 2. Take 2, plug it in for your x. Whatever that value is, you're going to subtract from 2.1. Whenever you do that, you'll get 0.38. For 3, you'll do the exact same thing. Take 3, plug it in for x, get your y hat value, take that number, subtract it from 1.5. When you do that, you'll get negative 0.54. For 4, you should get negative 1.37. For 5, negative 1.5. For 6, negative 1.32. For 7, negative 0.85. For 8, negative 0.08. For 9, you should get positive 0.89. And for 10, you should get 1.77. Okay. The resulting residual plot shows a strong pattern. All right, so these are our values that we had here. So if you'll notice, our x being equal to 1, we had a residual value that was 2.61. When our x was equal to 2, we had a residual value that was 0.38. When our x value was equal to 3, we had a residual value that was negative 0.54, and so on and so forth. So whenever you look at that residual plot, notice that you have a shape to it. You've got a definite pattern. You've got a pattern that looks like it's quadratic almost. So this pattern indicates that a nonlinear model may be a better fit than a straight line model. So the scatter plot of the original data, so this is the original data, so like your x being equal to 1, your y value was equal to 4. Your x being equal to 2, your y value was equal to 2.1. Your x being equal to 3, your y value is equal to 1.5. So whenever you looked at that original data, you can see that there's definitely like some sort of like non-linear pattern happening here. We can kind of like, if we were to trace this out, we would almost see something that looked kind of like this. And we can see that too in our residual plot. All right, example 4.6. Miles per gallon versus speed for a new model automobile is fitted with a least squares regression line. The graph of the residuals and some computer output for the regression are as follows. So we can see our residuals here. We can see that there's definitely a pattern going on in our residuals, and we have our computer output here. All right. In part 8, it asks us to interpret the slope of the regression line in context. So when we go back and we look at our computer output, our slope is going to be this piece right here. And so we've got a negative 0.218 slope. So the slope of the least squares regression line is negative 0.218, indicating that on average the miles per gallon drops by 0.218 for every increase of 1 mile per hour in speed. Okay, so B says, what is the mean predicted mile per gallon at a speed of 30? And so to do that, we would go back, we would check out what our entire equation was. And so our entire miles per gallon was equal to 38.9 minus the 0.218 times our speed. This time, remember, we're plugging in for our speed 30 miles per hour. So that means that we would take our equation, we would say miles per gallon hat equals negative 0.218 times 30 plus 38.929. And whenever you do that, you get 32.4. And so that would be 32.4 miles per gallon. C says, what was the actual miles per gallon at a speed of 30 miles per hour? So to use that, we're going to go back to our residual here. We're looking at miles per gallon. It appears to be right here. And so we have to kind of guess where we think that might be. And so if we think about this is 0, this is 10, right in the middle would be at 5. So right here at 30, we're almost to 5, not quite. We're definitely a little bit further away from 0 than we are from 5. And so I might predict that to be at like positive 3.5. So if it's at positive 3.5, and that's our residual. And remember, our residual equals our actual minus our predicted. And so our residual is positive 3.5. Our predicted value is 32.4. We would add that 32.4. We don't know what our actual is. That's what we're trying to find out. So we would add that 32.4 here, and we would get our x to be 3.5 plus 32.4 to be about 35.9. Which is roughly 36 miles per gallon. D says, is the line the most appropriate model, and explain? So to do that, we're going to go back to our graph of our residuals, and we're going to see if we had any kind of pattern to that residual plot. So when we look at that residual plot, we can tell that we've got kind of like a curved pattern to our residuals. There's not a random scattering. And so because there's not a random scattering, this line is probably not our most appropriate model. So we would say no. The residual plot shows a curved pattern. All right, E says, what does S equals 7.252 refer to? So if we go back and we're looking at our computer output and we find S equals 7.252, that's here, we've got to be able to interpret what that value stands for. So the S is the standard deviation. So the standard deviation of the residuals is 7.252. And so this number, the 7.252, kind of gives you a measure. So it gives a measure of how the points are spread around the regression line. And you can also think about this number being like a typical value of the residuals. Outliers and influential points. So in a scatter plot, regression outliers are indicated by points falling far away from the overall pattern. That is, a point is an outlier if its residual is an outlier in the set of the residuals. Scores whose removal would sharply change the regression line are called influential. So remember, when we were talking about this in chapter 3, we would have those points that would be like way far, either like up in the top corner or in the lower bottom corner, and they would kind of pull that regression line in their direction. By eliminating those points, it kind of evens out your regression line a little bit more and kind of gives you a better idea of like what an actual prediction line would look like. So we've kind of looked at a couple of examples where the straight line pattern maybe was not the best model for depicting a relationship between your two variables. And so sometimes the indications for that the fact that the linear model may not be the best would be if your scatter plot shows a distinctive curved pattern, or if your residuals show a distinctive pattern rather than having that random scattering that you need. And so in such cases, the nonlinear model can sometimes be revealed by transforming one or both of the variables, and then you can use a linear relationship. So useful transformations often result from using either the log button or the ln buttons on your calculator to create new variables, but there are lots of others that you could potentially see. So if you notice that your scatter plot has a distinctive curve pattern, or that your residuals show a distinctive pattern rather than just having random scattering, you may need to transform one or both of the variables in order to use a linear pattern. So, in example 4.7, it says, consider the following years and the corresponding populations. And so you've got your years, X, and you've got 1950, 60, 70, 80, and 90. And then you've got your population in thousands, which is your Y values, of 50, so 50,000, 67, so 67,000, and so on and so forth. The first thing it asks you to do is to show the scatter plot and the residual plot below. Okay, so if we wanted to show the scatter plot for this, we would need to make sure that we had our x-axis and our y-axis labeled appropriately. So I'm going to do the scatter plot first. So I've got my, oh, no, that's not it. I've got my y-axis and my x-axis. So my x-axis is going to be my year, and my y-axis is going to be my population. We're going to put it in thousands. So we'll do 50, and then we'll do 100, and then we'll do 150. And then for the year, we'll have 1950, 1960, 1970, 1980, and 1990. Okay, so for 1950, we'd have 50. For 1960, we'd have 67. For 1970, we'd have 91. And that one maybe is not a great place. Let me fix that one. Uh, 1980, you've got 122. And then 1990, you've got 165. So you can tell in our picture that we have almost, it's not quite linear, because when we see our 10-year gap here, we're a lot closer together than we are like for this 10-year gap. So it doesn't seem like there's the same amount of space in between each one. And so it appears that like if we were to kind of sketch this out, we would have almost like this going on. All right. It does ask us to do our residual plot though. So when we do our residual plot, remember our residual plot kind of looks like a T. So and so you still have your 1950, 1960, 1970, 1980, and 1990. If we were going to get our residual plot, we would need to go and get first our regression line. So we're going to go to Edit, clear out our L1 and L2, put our information in there with our X values being our years. And then our L2 being our population in thousands. So 50, 67, 91, 122, and 165. All right, so I want to go ahead and show you just because like the picture that we drew or that I drew was maybe not the best depiction, so we can see it on the calculator as well, so you can always do that. So whenever you do this, you want to go to second, y equals, so you make sure your scatter plots are turned on. I'm going to click on number 1, make sure it says on, make sure I've got my dot plot or scatter plot selected. And then I want to change my, make sure my X is L1, but I want to change my Y to L2. So I'm going to do second L2. Okay, so then when I'm going to go graph, and you'll notice that nothing pops up. Remember, you've got to do zoom and you've got to do non, so zoom stat. And so whenever you do that, you can kind of see a little bit better, maybe that you've got a little bit more of a curve pattern here. Okay, so if I want to do the residuals, okay, so because we want to get our residuals, we've got to have our prediction equation. So we're going to go to stat, we're going to go over to calc, we're going to do option 4. Our X is L1, our Y is L2, and then we're going to go to calculate. So whenever we do that, we get our equation to be Y equals 2.85 times our X value, which is going to be our years, plus negative 55 or 5,515.5. All right, so if we were going to use this equation to predict what we think would happen in 1950, we would say 2.85 times 1950 minus 5,515.5, and we would get 42. So we predict that in 1950 the population would be 42,000 people. Now, our actual was 50. And so if we wanted to find the residual for that, remember we take our actual and we subtract out our predicted, and we'd have 50 minus 42 to give us 8. Now, your calculator will do this for you. So if we were going to do this, we would hit stat, we would go to edit, we would go to L3, hover over L3, you're going to do second stat, and you're going to do option 8, which stands for residuals. So whenever you do that, notice that just like we predicted, or just like we said a minute ago, we took our observed value, which was 50, we subtracted out our predicted value, which was 42, and 50 minus 42 would give us 8. Now, if we took 1960, we plugged it into that same equation that we just used, we took that value and subtracted it from 67, we would see negative 3.5, and so on and so forth. All right, so we've got our residual values there. If we wanted to get our residual plot, we would do second Y equals. We are going to do, hit enter, make sure we've got our dot plot selected. We're going to make sure our X is L1 and our Y this time has to be L3. So if you want to change this, you're going to do second 3 to make it L3 because yours should say L2 right now. All right, so whenever you do that, you're going to hit graph. And whenever you do that, nothing's going to pop up because remember, you've always got to do zoom and then stat. So then you can see your residual plot. Now, remember, your residual plot needs to show random scattering, and it needs to be kind of balanced on the top half and the bottom half. So on this one, we can tell we don't have random scattering. We definitely have a distinctive pattern, and we don't have the same number on the top that we do on the bottom. So that tells us that we definitely are going to have to transform in order to be able to use a linear model. All right, so let's draw out what our residual plot would look like. Okay, so if we're drawing out what our residual plot looks like at 1950, let me go back. 1950, we want to go to stat, we want to go to edit so we can see our table again. At 1950, it was 8. So it would have been way up here. Okay, in 1960, it was negative 3.5, so it would be down here. In 1970, it was negative 8, so way down at the bottom. In 1980, it was negative 5.5, so still on the bottom, a little bit further up, not quite to that 1960 mark. And then in 1990, our residual was positive 9, so a little bit above where we were in 1950. So again, just like we said before, we've got definitely some sort of pattern here, some sort of curved pattern here, which tells us that we're definitely going to have to transform to be able to use a linear model. So notice that the scatter plot has a bit of a curve to it. So the original scatter plot kind of looks a little bit like an exponential function if you're familiar with exponential functions. Keep in mind that the inverse of an exponential function is a logarithmic function. And remember at the beginning when we first started talking about transforming, logarithms are one of the ways that we can potentially transform. So we can use this relationship, the relationship between exponentials and logarithms, to create a new scatter plot that has a much more linear relationship. So what we're going to do is we're going to keep our x values as our years in 1950, 1960, and so on. But now we're going to do log of our y values. Okay, so what I mean by that is basically doing log of 50. So if we do log of 50, we're going to do that on the calculator. So your calculator has a log button. The logs that we're doing are called common logs. Let me get out of this. The logs that we're doing are called common logs, which means they have a base of 10. So we're going to do log 50. And whenever you do that, you're going to get 1.698. So let's make it 1.7. Okay. For 1960, your original y value was 67. So we're going to do log 67. And that's going to give you 1.826. So let's make it 1.83. For 1970, your original y value was 91. So we're going to do log 91. Whenever you do that on your calculator, you should get 1.96. And then for 1980, you should do log 122. And that will give you 2.09. And then for 1990, you're doing log 165. And that'll give you 2.22. Okay, so now we're going to do a new scatter plot, and we're going to do a new residual plot. Okay, so just like before, we're going to do our x's as our years. Remember, you always want to label. So our years, 1950, 1960, 1970, 1980, and 1990. Our y values are going to be the logs of the population. Okay, so notice that we've got a little bit of a jump. So we're going to make that little mark that tells us there's a little bit of a jump. So we're going to do one of these guys. And we're going to start ours at 1.5 because we don't have any values that are lower than that. Our y axis is going to have kind of a small scale to it a little bit. We're just going to do 1.5. We're going to do 2.0 or 2.0, and we're going to do 2.5. Okay, so at 1950, we've got 1.7. So we're going to go like here. 1960, we've got 183 or 1.83. So kind of here. 1970, 1.96. 1980, 2.09. 1990, 2.22. So if you notice, this one has quite a better linear pattern. Okay, so that's a check. Now we're going to do the residuals. So remember, we make our T. So we got our residuals. Going to put our years. Okay. Okay. So we're going to go to L3. We're going to do log of our L2. Now, the reason we do our L2 is because, remember, we logged our y values, and our y values are in L2. So we're going to log our y values, and that's going to give us roughly the same thing that we just calculated when we were working in our table here. Okay, so like At 1950, my original value was 50. My transformed value was 1.699 or 1.7, right? Okay, so now that we've done that, we want to be able to use this L3 to be able to get our new regression equation that we can use because we transformed those values. So we're going to go to Stat, we're going to go to Calc, we're going to go to option 4 or option 8, whichever one you decide. We're going to do L1, but this time we're going to do L3. So you want to make sure you've got L3 as your Y because we're using that transformed Y. Okay, so now that we've got that, we're going to go to Calculate, and that's going to give us this equation. Now I want to point out that my R2 and my R are super close to 1. All right, so now that you've got that, we're going to get our residuals. So we're going to do second list. We're going to make sure our residuals are there. Hit enter. Okay, so we've got our residuals. Okay, so now we're going to go to Stat. We're going to go to Edit. We're going to go to L4, hover over L4, and we're going to put our residuals there. So second, Stat, residuals, enter. Okay, so now we've got our residuals there. Okay, we want to see our residual plot. So we're going to do second, Y equals to go to our stat plot. We're going to make sure our stat plot is turned on. We just put our residuals in L4, so you want to make sure your Y's are in L4, and then you're going to graph it. Now when you graph it, you're probably going to need to hit zoom stat so that you can see it, but you can see now we've got this random scattering on our residual plot. Some above, some below. Okay, so now we're going to put our residual plot on here. So we had a little bit above on 1950. Quite a good bit below on 1960, above on 1970, below on 1980, and right above on 1990. So just to confirm, that's coming from here. Okay. There are many useful transformations that you can use. So for example, you can use log y as a linear function of x. And so your new equation would be their predicted y value, or your predicted values would be log y hat equals ax plus b, and it expresses as an exponential. So that comes from the fact that if we rewrite a log, like in this case if we had this, our base would be 10. Remember that a logarithm is the inverse of an exponential, so we can go from logarithmic form into exponential form by kind of going in this like circle. And so this is how you would get 10 to the ax plus b equals y. So that's where this is coming from. Okay, log y is a linear function of log x. So say that we have to change, we've got to transform our y's and our x's. That's going to express as a power. And so if you have log y equals log 8 times log x plus b, just like before, you're going to do 10 to the ax, or a log x plus b, and it's going to give you your y. So if you did this, square root of x or y as a linear function of x would be solving for y, trying to get y by itself, squaring both sides. So that's how we end up with this. It re-expresses as a quadratic. 1 over y, solving for y, you would need to multiply both sides by y, and then divide by the ax plus b to get that by itself. And so it would re-express as a reciprocal. And y is a linear function of log x would be a logarithmic function. Y equals a times log x plus b. Note that although you need to be able to recognize the need for a transformation just by, so you can justify it by its appropriateness by a residual plot, use whichever is appropriate from above to create a linear model, and use the model to make predictions. You do not have to worry about how you re-express, so you don't have to worry about these pieces right here. But you do have to know when it's appropriate to do a transformation and which transformation would be appropriate. All right, so on example 4.8, what are the possible models for the following data? Okay, so we've got x values of 1, 2, 3, 4, and 5. We've got our y values there. And so let's first start with looking at what this would look like just on a scatter plot. Okay, so we would make our x's and y's. We don't really have to give them any fancy labels, just x and y. Make sure you've got your x's as 1, 2, 3, 4, and 5. And then your y's, maybe based on this, we go by 50s. Okay, so 1 was at 20, so kind of low. 2 is at 60. 3 is at 120. 4 is at 190. And 5 is at 280. So when we look at this, we can tell we've got a little bit of a curve, which tells us that a linear model is maybe not our best approach at finding a line of best fit. So we're probably going to need to transform. Okay, so we're going to just try some stuff out, see which one works the best. All right, so that's kind of what you're going to need to do. You're just going to kind of guess and check and see which one works the best. Okay, so let's start first with just doing log y. Okay, so if we did log y, so I'm going to go to my stat. I'm going to go to edit. I'm going to get rid of all this stuff because I don't need it. So we'll put our new values in there. So we've got 1, 2, 3, 4, and 5. And then our y values are going to be 20, 60, 120, 190, and 280. Okay, so we're going to start with logging our y values. So we're going to say log of L2. Okay, so now we're going to get our new equation. So we're going to do, now that we've logged, now we can try to do a linear. So we're going to do our linear. We're going to make sure we do our y list as L3 because that's where we transformed our data. So we get this. We can see our r squared and our r are still not quite to 1 where we want them to be. But we'll see what's happening with our residual plot. All right, so I'm going to go get my residuals. So I'm going to do second stat to get my list. Do residuals. Hit enter. Okay, so now we're going to go to edit again. And then in L4, we're going to put our residuals. Okay, so now we want to do our residual plot. I already have my y as L4, so that's good. I'm going to go to graph and zoom step. Okay, so we can see that that's maybe not our best option because we had, so this is by doing log y. So our residual plot, low, high, higher, lower. Medium. So that one's out. Okay, so now you're going to clear out everything that you've got in your L3s, L4s, L5s, all that stuff. Okay, so we just did one where we logged our Y's, and we saw that our residual plot for that showed a distinct curve pattern. Now, we already knew that the original, like the very original, was not going to work because it had the scatter plot itself had a little bit of a curve. If we had done the residuals, we would have seen a curve pattern to that as well. So a linear model that has not been transformed is not going to work, and just logging y is not going to work. So if we find that just logging y is not going to work, then maybe we can log x and log y. Okay, so if we log both of them, logging x and logging y is what we call a power regression. And so if you look back on the piece that we just talked about here at the top, it says that. So if we log y and we log x, that it re-expresses as a power. Okay, so the good thing about that is your calculator will do everything for you. So this is going to be log x and log y, and we call that power regression. Okay, so you're erasing everything that you've got in your calculator except for your L1 and your L2. So your L1 should be your original x's, your L2 should be your original y's. Okay, so now we're going to do stat, we're going to do calc, and we're going to do a power regression because we want to try logging x's and logging y's. Now, you can go through the process of finding the log of your x's and finding the log of your y's, but your calculator will do all that for you, so it just makes things a little bit easier. Okay, so we're going to do power regression. Your x's are your L1s, your y's are your L2s, and then we're going to go to calculate. So when we calculate, we're going to get our equation here, and then we want to go get our residuals. Okay, so we're going to do second, stat, get our list, do our residuals. It'll calculate those for us, and then we're going to go put them in our L3. Okay, so we're going to do stat, or second stat, residuals, enter. Okay, now we want to get our residual plot, so we're going to do second y equals, get our residual plot. We want our x's to be our L1s, and we want our y's to be our L3s, and then we're going to do zoom stat. So whenever you do that, notice that you've got some random scattering. Definitely no pattern to it, no curved pattern to it anyway. And so we're good to go. All right, so we're going to make our residuals. And I didn't label this one. I needed to label this as residual. Okay, so we're going to make our T. Label the side as residuals. Make sure you've got your 1, 2, 3, 4, and 5. And then you're going to mimic this that you've got on your calculator. Oh, actually, these changed. I didn't think about that. All right, so these changed because we are logging our x's and logging our y's. Okay, so the first one, this essentially would be log of, actually, no, it won't be that. This is going to be log 1. And the reason that log 1 is going to go here instead of the first place is because if you do, let me get out of this, if you do log of 1, you're going to get 0. So we're going to start it here. Okay, so at log 1, which is 0, let me go back to my residual plot. You were right here. Okay, so here. Okay, And the reason that your calculator recognizes it, doesn't put it on the x-axis, is because this is still 1, this is still 2, this is still 3 in your calculator's mind. All right, now we're going to do this one as log 2. This was 0. This is going to be down here, so I'm going to go ahead and put that here. But log of 2 is going to be 0.30. So this is like 0.3. Okay, this one is going to be for log 3. Log 3 is at like 0.4, let's make it 0.48. And so you can see here, it's about right there. Okay, so we're going to do log 4, 0.6. And that one was at the bottom. And then the last one will be for log 5. .7. And at log 5, or at our 5th one, we were up here. Okay, so in summary, a scatter plot gives an immediate indication of shape, linear or not, strength, and direction of a possible relationship between two variables. If the relationship appears roughly linear, then the correlation coefficient R is a useful measure. So if we are looking at our scatter plot and it seems like our points are kind of making a line, then we can use that R. Your R is always going to be between -1 and +1, with positive values indicating positive association and negative values indicating negative association. Values close to -1 or +1 indicate a strong linear association, or a stronger linear association than values close to 0, which indicate a weaker linear association. Evidence of association is not evidence of cause and effect relationships, so that's one of the biggest important things about this section. Correlation is not affected by which variable is called X and which is Y, or by changing the units. Correlation can be strongly affected, however, by extreme values. The difference in your observed and your predicted values is called your residuals. Remember, you always find them by saying observed minus predicted. Your prediction line is the best fitting straight line called the regression line, and it minimizes the sum of the squares of the residuals. Remember that for linear regression models, the mean of the residuals is always 0 because the sum of the residuals is always going to be 0. A definite pattern in the residual plot indicates that a nonlinear model may fit the data better than a straight regression line. The coefficient of determination R squared is going to give the percentage of variation in Y that is accounted for by the variation in X. Remember, those influential scores are scores whose removal would sharply change the regression line. So those influential scores are scores that are going to pull your regression line in their direction. Nonlinear models can sometimes be transformed by transforming one or both of the variables and then noting a linear relationship. And it is important to be able to interpret generic computer output. Remember that your AP exam will definitely have that on there. So you've just got to be able to pick out what the pieces are and what they mean.